In the previous video, we wrote down the power series expansions for sine and cosine. In a future slide deck, we will use these series expansions to demonstrate a beautiful relationship called Euler's formula. For now, we will show how the power series representation for sine can be used to approximate pi to 4 decimal places. Sine of theta is a sum of increasing odd powers of theta divided by the factorials of the powers with alternating pluses and minuses. In the video on trigonometry, we drew a series of right triangles to approximate pi, including this right triangle with hypotenuse of length 1, subtending an angle of pi over 6, with legs of length 1/2 and root 3 over 2. Sine of pi over 6 can be evaluated by substituting pi over 6 into the power series. The sine of pi over 6 is also the length of the leg opposite the yellow label for the angle pi over 6. This length is 1/2. We know that pi is roughly 3, so pi over 6 is roughly 1/2. Since pi over 6 is less than 1, the higher power terms in the power series are relatively small. Adding successive terms, as symbolized by the ellipsis, corresponds to adding small and even smaller quantities. Pretending that the ellipsis can be neglected, multiplying both sides by 6, explicitly evaluating the factorials and then moving some terms around, we find that pi is approximated by 3 plus pi cubed over 216 minus pi to the 5th power divided by 155,520. We will approximate pi through iteration. We know that pi is somewhere around 3. We can put this value of pi into the right-hand side of the equation to get 3 plus pi cubed, that being approximated by 3 cubed divided by 216, minus pi to the 5th power, that being approximated by 3 to the 5th power, divided by 155,520. Using a calculator or longhand arithmetic, this calculation yields 3.1234. We adopt 3.1234 as our next starting guess for pi, which can be substituted again into the right-hand side of the expression to obtain a sum of 3 terms that together equal 3.1392. Continuing 3 more times, the successive approximations to pi start to settle down until they reach the stable value 3.1416, which is consistent to 4 decimal places with our mnemonic sine, sine, cosine, sine 3.14159. In this slide deck, we have discussed how a function could be represented by adding terms together in a power series expansion. While it is mathematically interesting that this strategy is suitable for accurately imitating a variety of functions in the vicinity of various expansion points, a common physical motivation for using power series representations is that power series expansions often remain useful even when they are truncated so as to contain only a handful or even a couple terms. In this video, we show that the first 3 terms in the power series expansion for sine in the vicinity of theta e equals 0 were sufficient to allow us to calculate pi to 4 places beyond the decimal point. In the first 2 videos in this slide deck, we developed a conceptual foundation for understanding power series expansions. In the first video, we developed the notion that higher-order derivatives describe geometric properties of plots of functions, and in the second video, we showed how binomial terms and coefficients could be combined to construct a series representation for a function. To reinforce the understanding we developed, we worked through practice examples in the final 2 videos in this slide deck. In the third video, we obtained a power series expansion for sine, and in this fourth video, we truncated the power series to obtain a power series approximation that we used to obtain pi to 4 decimal places. Just as decimal representation allows us to truncate a price so as to neglect corrections smaller than a cent, using a power series expansion is often useful for truncating terms in order to simplify an equation that describes the time evolution of a dynamical system, for example, to simplify the study of molecular interaction networks. We will develop this idea further in the chapter on differential equations.